Hello, everybody. My name is Jonathan, and I'm a second-year master's student here at OSU. I'm studying systems programming and security with the amazing Dr. Yangjun Zhang. And I'm also a member here of OSUSEC. I play CTF, so if you ever come by for some of those, you might see me there. And one of my hobbies over the past few years has been speedrunning the 1994 Super Nintendo game Super Metroid. And this last spring, I had the opportunity to work on a tool-assisted speedrun of this game. It is the fastest known completion of the game, and it beats the game by using, essentially we abuse programming errors in the game engine to take full control over the program's execution and use that to just skip directly to the end of the game without having to play through most of it. I am going to be recording this talk and putting it on YouTube so I can share it with the broader Super Metroid community. So if you're watching through that, hello, good to see you. You probably know me by my Discord tag, Nobody Nada. I also did not work on this alone at all. I worked together with a legendary veteran Super Metroid TASer named Snick. Snick is an absolutely awesome person to work with. Total genius. He found most of the glitches and the skips and the techniques that we used. He did most of the movement and the optimization in the run. My role was just putting everything together, figuring out how to turn these glitches from weird bugs that crash the game into actual full code execution. So I assume most of you guys have at least some familiarity with the idea of speedrunning. That is, like, trying to beat a video game as fast as possible. It's not that complicated of a concept, but there are some details that come up when you actually try to start speedrunning that you have to address. The most important one being, what does it actually mean to beat the game? Like, what's our objective here? For example, if you're playing like Super Mario Brothers, is your speedrun valid if you skip some of the levels with warp zones, or do you have to play all the levels? Or in Super Metroid, which has a bunch of items hidden throughout the game world to collect, and only some of the items are necessary for progression. Can you skip the items you don't want or need, or do you have to collect all of them in order for it to count? And how do you rank runs that do it differently? Like if I beat the game collecting all the items, and you get a faster time than I do, but you skip some items, who wins? And the answer to that is that the leaderboard is separated into categories based on how exactly you want to play the game. For Super Metroid, some of the most popular categories are any percent and 100%. The naming comes from the fact that at the end of the game, you get a percentage that shows how many of the items in the game you collected, so you can figure out if you missed stuff or if you got everything. And for the any percent category, all you have to do is get to the end of the game. Any percentage on that ending screen is acceptable. That's the name, any percent. The world record for that category is 40 minutes and 36 seconds by a runner named Oats and Goats. Whereas for the 100% category, you still have to beat the game, reach the credits, but you have to collect all the items along the way. So if you beat the game and it doesn't say 100% at the end, then your run is not valid. The world record for that category is an hour, 12 minutes, and 40 seconds by a runner named Shiny Zenny. That's wrong. That is out of date. It is, as of a week or two ago, it's a minute, 12 seconds, and hour, 12 minutes, and 30 seconds. I apparently did not update this slide. I've had to update this slide several times since I made it. Both of these records are new since I made the slide, which is absolutely awesome. The Super Metroid community is super active and full of really cool people who are just trying to push the game further. Also, fun fact that you might not have known, you might have heard like any percent, 100% terminology in reference for video games before. You may not have known that that is a direct reference to Super Metroid, being one of the earliest speedrunning communities, and since the game, when you beat it, it shows you a completion time and a completion percentage. That's actually where that terminology originated in the broader video gaming community. But both of these categories have a restriction that we need to mention. And it's that these runs were achieved without the use of any major glitches. So a major glitch in Super Metroid is defined as something that just completely breaks the game, like corrupting memory or going out of bounds or anything where just the normal rules of the program just no longer apply and stuff totally goes off the rails. You're not allowed to do anything like that in these standard any percent or 100% categories. But there's a separate category called any percent glitched, which is any percent, you just have to reach the credits, but anything goes as far as glitches. You can do, as long as you're not like modifying your hardware or something like that, you can do anything you like to beat the game, as long as you actually beat the game. The world record for that is 11 minutes by a runner named Gruya. But there's one more restriction in here that seems obvious, but it's also a restriction that we can play the game without. And it's the restriction that you actually have to have an actual person playing the game on a controller. Which means that you're limited by how fast somebody can press the buttons, like how accurately and how consistently can they actually play the game. If we relax that restriction, we get what's called a tool-assisted speedrun, which is what Snick and I worked on. And the goal of a tool-assisted speedrun is reach the credits, except you don't actually have to have a person playing the game. You have a computer either hooked up to your console or running in an emulator that is feeding inputs into the game. And our record, according to the same timing method that all these other runs are timed by, is 3 minutes and 47 seconds, which is, as you can see, significantly faster than either of these times. So what actually is a tool-assisted speedrun? Like, how do we make one? And essentially, the definition is you're doing a speedrun, but instead of playing the game in real time, we script out a sequence of inputs frame by frame, and then we have the computer play them back for us. So if you say miss a jump or something like that, in a real speedrun, you have to figure out where to go from there. What do you do next? In a tool-assisted speedrun, you just go back and you change your input file so that you didn't miss the jump. Essentially, a tool-assisted speedrun is kind of like a theoretically perfect speedrun. Like a fully optimized, fully complete task is basically the fastest theoretically possible known way to beat the game. In order to beat the game faster than the tool-assisted speedrun we have created, you would either have to discover a new glitch, or you would have to figure out a new way to move around faster that we didn't think of. In order to create a tool-assisted speedrun, you use a program called a recording emulator. The emulator we used is called LSNES, and it gives us the ability to record and replay sections of the gameplay. We have save states so we can jump around in time. We have the ability to slow the game down, maybe run it frame by frame, rewind, fast forward, and then also more advanced features that you might be used to for programming, like input macros, or having some kind of version control system on our input so we can test different strategies to see which is faster. Also debugging features. We get the ability to introspect memory and processor state as the game is running. For example, we can have it highlight important variables on the screen. We can look at memory in a hex editor. We can have it log all the instructions and CPU registers as the game runs. So we have full visibility into everything that's happening inside of the hardware, and we can figure out exactly how the game's code is working and how our inputs are affecting it. So yeah, with that, let's go ahead and watch the run, now that you know what we're actually doing and what we're working with, and then we'll talk about how it works. So one thing to note is that I am skipping, in this video, I'm starting playback after Series Station, which is kind of the tutorial area of the game. The reason for that is because there's not really any big glitches or interesting tech that happens in series. It's just movement. That's not to discount the work Snick did there, because he put a ton of time into making series fast, and I feel really bad that we don't get to watch it. So go watch it on your own time after the talk. If you're not familiar with Super Metroid, the game is a Metroidvania. This game is such a good game, but there is a genre named after the game. The basic way that this game works is you have a big open world, and there's a bunch of obstacles throughout this world that you can't get past. And then there's items hidden throughout the world in secret areas that let you overcome these obstacles. So the game's all about exploring, backtracking, finding secrets, and using them to get past obstacles. The last thing to note is that I've overlaid the controller input in the top left there, so you can see the the precision and the speed which we're pressing the inputs. Yeah?
Yo, what? I noticed the character was shooting a randomly bolt falling. Is that?
I will get into that. I'll get into that in a little bit. It's called a moonfall.
Oh.
And that's time. We've just beat the game. This is the ending cutscene. So as I said before, this is the fastest known completion of this game. But according to standard task timing, which is from power on until the last input, that was 6 minutes and 12 seconds. By the standard speedrun timing, which is start of gameplay to the last input, that was 3 minutes 47 seconds. And according to the game's in-game timer, which only counts gameplay, not like cutscenes or doors or lag or anything like that, it was 1 minute and 58 seconds. That also makes this the first ever run in less than 2 minutes of in-game time. So,
Wait, what?
yeah, that's in minutes, not in seconds. So it's hours, minutes. So it's saying it's taking that 1 minute, 58 seconds, and then it just truncates it to 1 minute. But yeah, what happened there? Let's get into that. So starting with a bird's eye view, this is a map of the whole game world.
Question.
Yeah,
Can we turn the lights down so we can see the screen better?
I don't know how to do that.
I can in a sec.
Awesome, thank you, Casey. This is the map of the whole game. We start, Samus's ship starts right up here, that red circle up at the top. And we identified this room over here as having the necessary conditions for our exploit to work. So those rooms that's not that far spatially from the start of the game. But remember, this is a Metroidvania. It's all about backtracking and finding secrets and exploring. So the developer intended route to get from point A to point B looks like this.
Oh shit.
Whoa.
There's a lot of exploration, a lot of backtracking. That would take forever. So we're just actually going to skip most of that. There's actually only 3 obstacles that block our path from directly going from point A to point B. The first one is this wall here, which you need bombs in order to break. Bombs, in order to get those, you have to fight a mini-boss. In order to fight the mini-boss, you have to have missiles. In order to get missiles, you have to have morph ball. In order to get morph ball, you have to go down an elevator and go do all this exploring stuff. It takes a while. So instead, we're just going to clip out of bounds. We're going to do that using a technique called a door skip. The idea is if we frame perfectly, unpause the game, and activate a door transition at the same time, then we can actually fall through the door. The reason for this is because of a race condition in the game. The way the game's main loop is structured is there's this giant switch case statement that runs once per frame, and it switches over a variable called the game state that tells, like, at the very highest level, what exactly do we need to process this frame. This game state can take on values like title screen, or file select menu, or pausing, or unpausing, or normal gameplay, or door transition, loading the next room. And when we unpause the game doesn't just unpause instantly, it sort of fades in, and then it's fully, when the screen's fully brightened, it's done unpausing. When we touch a door tile, it sets the game state to going through a door, which will start the game loading the next room on the next frame. But if we unpause on that same frame, if the unpause animation, the screen brightening finishes, then that overwrites the loading the next room value that just got set in there. And so we just fall right on through the door and end up out of bounds. Once we are out of bounds, we almost immediately go to the next room, which is the room on the left side of those bomb blocks up there. How do we do that? Well, the idea is that the game stores level data as a two-dimensional array in memory, and it's stored row by row. So the top row of the room is stored first, and then the next row is stored in memory immediately after that, and then the next, and then the next, all the way until we get to the bottom of the room. There are no bounds checks on Samus's position when accessing this 2D array. That's because the developers expected that the level design would keep the player in bounds. Like, they're not going to go and just put holes in the floor for you to fall through out of bounds. Except that with door skips, that's what doors are. So because there's no bounds checks, if we go below the bottom of the room, if we go below the bottom of the 2D array in memory, we're going past the end of it, and it's a buffer overflow. We end up in basically garbage uninitialized memory, whose values depend on whatever the game last stored there. And while we're out of bounds, like the bytes of memory out of bounds get treated as tiles. And so some bytes will be solid, some bytes will be air, some bytes might be spikes or items or doors. And so in order to get through that door on the left of the bomb block, what Snick did was he found a very fast and efficient route, navigating tiles out of bounds in order to find a byte that had the same tile ID as the door on the left side of the bomb block. So we hit that, and the game thinks we went through that door. Now, one thing about going out of bounds and hitting doors out of bounds that's sometimes convenient and sometimes not is that when we hit a door from like the wrong spot, it oftentimes places us somewhere out of bounds in the next room. In this case, that's actually really convenient because in the next hallway we end up with, we don't have to run through the hallway. We're just out of bounds, and so we can find another out of bounds door block and use that to just not even have to run through the hallway. So as you can see, the screen, after we get out of bounds, the screen fades in with the next room, and then within like a second, we found a door block out of bounds, and we can go into the room after. Once again, this door placed us out of bounds, but this one's different. Before we went out of bounds below the room, this time we're out of bounds to the right of the room. And since this is a 2D array, if our X position overflows and we go past the end of one row, then we end up in the next row. So a way of visualizing this is that if you're over here and you go out of bounds this way, then it's like you've wrapped around down to the next row on the other side. In this room, that means we can just traverse the room normally, except way off to the right. We're sort of traversing almost like there's this shadow copy of the world off to the right. The Super Metroid, or the Super Mario 64 speedrunning community calls these parallel universes. We don't usually use that terminology in SM. We just call it like copies or something like that. And you can actually see, you can see us based on how the screen is scrolling, that we are just traversing the room. And you can also see that the pirates are shooting way off to the right side because that's where we actually are. We're way off to the right. Now, in this room, finally we're actually back in bounds again. That door transition did what it was sort of supposed to. But this room is really long. We can just run through it. That works. But it's actually faster to do a door skip if we go through the right door and we do a door skip. We go out of bounds to the right of the room, which causes us to immediately trigger the door on the left. So that's a way faster way of traversing the room. Here we do a pause, frame perfect to unpause as we hit the door, and then it scrolls us to the left. We end up out of bounds in the elevator room, but we're just out of bounds to the right, and so we can stand on sort of the shadow copy of the elevator off to the right, and when we activate it, the elevator just warps us back in bounds. So that's all we did to get past the bomb blocks. Our second obstacle is power bomb blocks. And the power bomb blocks are supposed to block us from getting through this floor until like a third of the way through the game. Basically, this is a room you can access fairly early in the game, and then the idea is you can come back later on once you have more items and you can do more things here. The good news is that clipping through blocks vertically is way easier in this game than clipping horizontally. You asked a minute ago about why we were firing shots while falling. That is a technique called a moonfall. It was discovered by Snick in 2017. It turns out that because of some some lovely programming that we'll get into a little bit later. If you do a spin jump while turning around, while firing a shot, while aiming diagonally, while moonwalking backwards off a ledge, then Samus falls with no terminal velocity. You just keep building up more and more and more fall speed as you fall. And as you build up speed, eventually you get enough speed that you can clip through blocks. So here we do a very fast moonfall. We clip right through the powerbomb blocks. And then we just do another moonfall just because this room is so long, it saves time to do it. And then the last obstacle is, of course, the spiky tunnel. That you're supposed to have Morph Ball to be able to roll through. We don't have Morph Ball. So Snick came up with a pretty precise sequence of inputs that lets us do some like hitbox manipulation, some damage boost stuff to just sort of like finagle our way through without taking too much damage. Then we do a couple damage boosts, weird jumps, and the game just breaks. So this is the point at which we have to stop thinking about this like a speedrun, and we have to start thinking about this like a CTF, like a binary exploitation challenge. And the first step of any binary exploitation challenge is going to be figuring out how the game works, like what's actually going on under the hood. How are we going to exploit this? And if we have any CTF players in here, when you start a Pwn challenge, you go to the leaderboard, you download the challenge handout, and you get some binary file, what is the very first thing you do with this binary?
You run it?
Well, in order to do that, you have to know how to run it.
True.
So there's at least a step, I don't know if everybody does this, but there's a step I do before that. What's that, Lucas?
File it.
Exactly. The first thing I always do is I run the file command, because that'll tell me what kind of binary it is. Like, what kind of processor does this expect to run on? What kind of operating system does this expect to run on? You can't start reverse engineering until you understand the hardware. So we don't have to run file. We already know Super Metroid is a Super Nintendo game. But we do have to understand a little bit about how the Super Nintendo works under the hood. So the CPU of the SNES is the WDC65C816. This chip is a 16-bit extension of the 8-bit MOS 6502. Some of you might be familiar with that processor. It's a very famous chip that was used in all kinds of home computers during the 70s and 80s, including the original Nintendo Entertainment System. Now, the 65C816 is a 16-bit processor that has a 24-bit memory address space. This means that like all of its internal registers and stuff are 16 bits. Pointers are 16 bits, but it has 24 bits of addressable memory. And that works kind of similarly to x86 memory segmentation. If any of you guys are taking OS2 or have taken it in the past, where the address space is broken up into different chunks that you can activate by setting a register in the processor. In this case, those chunks are called banks. The processor has 8-bit bank select registers that determine what bank is active, and then within that bank, you have 16-bit pointers. So this is a diagram of the system's physical memory map. There's only a physical memory map because there's no virtual memory on this system. The x-axis here, these numbers at the top, indicate the bank. And then the y-axis here, these numbers on the side, indicate the address. So the game does most of its work in like these banks over here. So we'll focus on those. Addresses hex 0 through hex 2000 are memory, just RAM. Addresses 2000 through 6000 are memory mapped I/O registers. And then hex 8000 through FFFF are the cartridge ROM. So if you're not super familiar with memory mapping and MMIO and all that, this might be a little bit of a new concept to you. The idea here is that not every memory address actually refers to RAM. This first bit refers to actual RAM on the system's RAM chip, but this section here is mapped to the game cartridge. And so this means that the game can access data directly off of the cartridge as if it was in memory, and you can execute code directly off the cartridge without having to copy it into RAM first, because it's just mapped. And this I/O space here, the 6502 family of processors has no dedicated like input or output pins or ports like x86 does. Instead, all communication with the outside world is done through the memory interface. And so basically what this means from like a programming perspective is, or a reverse engineering perspective, is when you're looking through code, when you see a read or write in this region, this 2000 to 6000, that means that it's not actually going to memory. It's not gonna like just save a value there that you can read back later. It's controlling some kind of a hardware. It's sending a command or receiving data from some external hardware. So some of these addresses will, like when you write to them, it'll have some kind of a side effect, or it'll trigger some operation to happen, or it'll do something, or it'll give you some status of some external hardware that's connected or something like that. There's registers for controlling graphics in here. There's registers for controlling sound. There's also registers for reading from the controller. So this means that that the controller input, like the buttons that we're pressing on the controller, are mapped to a physical memory address that the program can read. So to understand the I/O space a little bit better, let's look at a block diagram of the rest of the SNES. This is kind of a simplified diagram. It's more of a software engineer's perspective than a hardware engineer's perspective. Like, these blocks on this block diagram do not correspond one-to-one with chips on the motherboard, but they correspond with like functional, logical components of the system. So we have our CPU, and the CPU's only communication with the outside world is through its memory bus. On this memory bus lives, as we mentioned just a minute ago, the system's internal working memory, the external cartridge connector, and I/O hardware. Within this I/O space, we have an I/O controller that'll send our requests out to external devices like the controller, or the picture processing unit, or the sound processing unit. Now note also that the PPU and SPU have their own memory that's on its own bus, distinct from the CPU's working memory. This is basically the same idea as when on a modern computer system, your graphics card has like its own discrete memory that's, as opposed to like a system with integrated graphics memory. This means that the PPU has exclusive access to all the graphics related stuff, and it can freely access that memory whenever it wants without having to compete with the CPU for bandwidth. So this is a performance optimization. I also want to point out that this means that it's a little bit more complicated to like get data into there, because you can't just directly write data into graphics memory. You have to go through I/O registers and stuff like that. The I/O controller has a feature called DMA, or direct memory access, that allows you to very quickly transfer data from either work RAM or the cartridge to any external I/O device, like the PPU or SPU. And so that's really commonly done for, like, when you have some graphics data that you want to upload, the fastest way to do it is to feed it to the DMA controller, and the DMA controller will just quickly send it over there. One thing to be aware of, compared to a modern system, there's no bus arbitration on the SNES. So on a modern computer system, when you have devices that are sharing memory buses like this, you have the idea that when multiple devices try to access the bus simultaneously, then they have to take turns. Like, the bus can't service multiple requests at once. They have to go one after the other. And this is done using bus arbitration hardware. On the Super Nintendo, there is no bus arbitration. If two devices try to access the bus simultaneously, you get some kind of a conflict and stuff breaks. So it is the responsibility of software and hardware designers to ensure that never happens. For example, that DMA controller that I talked about a minute ago, that can quickly copy data from internal RAM or cartridge ROM to something like VRAM or ARAM, it actually disconnects the CPU from the bus while it's running. So the CPU, whenever a DMA transfer is active, the CPU is suspended, and the I/O controller has exclusive access to the CPU bus. Sometimes you have to do this in software, though. For example, it is just in the documentation that you are not allowed to try to access video memory or audio memory. Well, audio memory is a little different because you're writing a program that runs on both ends. We're not going to get into that. But with video memory in particular, you are not allowed to touch video memory while the PPU is rendering. You just have to be sure that you time it so that all of your video memory accesses happen during what's called a blanking interval when no pixels are being generated. The blanking intervals, there's a vertical blanking interval that happens in between frames. And there's also a horizontal blanking interval that happens between each line of one frame, between one line and the next as the PPU is rendering, because it renders from top to bottom. Another thing to note that's related to that is that there is no frame buffer in this system. This was back in the days when memory was really expensive. You couldn't just store a whole image in memory. And so the PPU is actually designed to generate pixels on the fly as they are scanned out to the television. That combined with that horizontal blanking interval allows us to do some interesting effects. So the DMA controller has a feature called HDMA or H-blank DMA, which allows us to schedule a DMA transfer for some point in the future, specifically during an H-blank at a certain point in the rendering process. So for example, the game needs to draw the status bar with completely different settings than the rest of the gameplay. So at the beginning, it sets up all the PPU's configuration registers to draw the status bar, and then it schedules an HDMA transfer for right at the end of this line, in between basically this line and this line, so that at that point, the DMA controller will suspend the CPU and then automatically copy over the new configuration data so that the PPU is configured to draw the gameplay instead of the status bar. This is also done to create like special effects. On this title screen, this gradient in the background is done with HDMA that periodically changes the blend color as the PPU moves further down the picture. This like security camera effect over here is done using an HDMA at the end of each line that changes the horizontal position and width of this beam to create a beam that does that down the screen. And then also over here, it's probably kind of hard to see on this projector, but there's like this heat wave effect going on in the background. That's done using HDMA to continually like modulate the scroll between each line. And then also this rising lava is done using an HDMA at whatever the height of the lava is to turn on the lava at that height. Let's move on from hardware stuff and let's talk about the game engine a little bit. Specifically, we're going to talk about how Samus's movement works. So Samus's movement in this game is represented as a finite state machine, where each state is a pose. That's something like, that describes like an action Samus is performing. Like, those are some examples. Facing right, crouching, aiming down right. Moving left, gun extended. Facing left, landing from spin jump. So each one of those is an individual pose. They're all like hyper-specific. There are 253 different poses in the game. And every time you press a button on the controller, the way that that's processed is it triggers an edge in the state machine. So the nodes are the different poses, and then the edges represent different buttons that you can press that'll transition you to a different pose. So being a CS student, you know, we've all done like finite state machines and stuff. So when you see a finite state machine, you immediately want to go plug it into GraphViz and see what it looks like, right? So after like a couple minutes of processing, this is what GraphViz. So yeah, that's not going to be very helpful. And that's actually pretty incomplete. That only considers post transitions that happen in response to us pressing a button on the controller. There are many more ways that we can cause post transitions. For example, taking damage, getting grabbed by things that can grab you, interacting with things that you can interact with, colliding with things you can collide with, getting hit by like projectiles, using your grapple beam to swing off of blocks. Different cutscenes can trigger post transitions. If we wanted to account for all that in our GraphViz diagram, we'd have to add like thousands more edges. And this is actually a really good design in that it's a very natural model for how Samus moves around. Like, you know, you're running, you press the jump button, you start a jump, and the movement in this game feels really good because of just the sheer number of different poses that there are and the number of transitions between them. You have an enormous amount of options for how you want to move Samus, and that makes it a really fun speed game, just because of how intricate the movement is. But like, when you read the code, you can really feel how it started out as like this nice, elegant, simple design, and then they started to like add more features and add more poses, and then they'd find bugs that they'd have to fix, and they'd have to add this special case to handle this cutscene, and then they'd have to just keep making all these changes, and design requirements were changing, and the release date was approaching, and the code just like it pretty clearly just devolved as the project went on. And the result is that like it's got some bugs. It's got a lot of bugs actually. So, yeah, we're gonna look at one specific pose bug in a lot more detail here. But in order to understand it, we have to talk about animations. So every pose has associated with it an animation that defines the visual appearance of Samus during that pose. An animation is defined as a sequence of one or more animation frames. An animation frame has two things associated with it: a sprite map that defines how Samus looks, and then also an animation delay. The animation delay normally indicates like how long that sprite map should be shown before you go to the next frame of the animation, but it can also do special things. It can have special values that tell the animation to loop or to do some kind of like a conditional behavior, like maybe if Samus is holding the run button, then it'll switch to a different animation sequence or something like that, or some kind of special like interactions with tiles or cutscenes or whatever. Animation instructions can do a lot of different things. One of the things that they can do is pose transitions as well. So this is an example of an animation. This is the animation associated with pose hex 19. On the 6502 family of processors, it's conventional to notate hex with a $sign instead of a 0x. So that's what we'll do for this presentation, just for consistency with the rest of the 6502 world. So this animation has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 frames associated with it. The first frame is this sprite, which is Samus like starting a spin jump. And then the next 8 frames are the different frames within the spin jump. And then this last frame here is a special loop instruction that indicates that at this point, the animation should loop back to this frame. So when you do a spin jump, you get this transitional frame first, and then you just get these 8 frames in an endless loop until you're not spin jumping anymore. A different example of an animation is the turning around animation. So this pose is hex 2-5. It is the standing turning left to right pose. So Samus starts facing left, and then she turns around and faces right. So this is implemented using these 3 frames that actually display the animation. And then the 4th frame has a special instruction that says, once you reach this point, don't continue with this pose. Actually transition to a different pose, the standing facing right pose. Now, I've thrown out that word sprite map a couple times. Every animation frame has a sprite map, or at least most of them do. Some of the special ones don't have sprite maps. What is a sprite map? Well, it's a list of tiles to be drawn on the screen in the form of sprites. See, with 253 poses and each pose having its own animation, that would be a lot of sprites. And so what the animators did is they broke Samus into little tile chunks. That each tile is just a little thing like a piece of her arm, or her visor, or her helmet, or her gun, or her legs, or her torso, or something like that. And then these tiles are composited together using sprite maps. A sprite map defines just a list of tiles and how they should be arranged. So the format of a sprite map in memory, it starts with a 2-byte word that indicates the number of sprites in the sprite map. 2 bytes is a lot. That can hold up to 65,000. Typically, a sprite map is going to have something more like 5 sprites in it. But the reason why they use 2 bytes is because it's a 16-bit processor. That's the natural word size. It made the code faster that way. Then, after that 2-byte number of sprites in the sprite map, there are 5-byte sprite map entries. Each entry has an X position, which is an offset from the center of the sprite map, a Y position, also an offset, and then attribute bits for things like color palette and priority flags, and then also the tile ID that defines the visual appearance of that sprite. In order to actually draw a sprite on the screen, the sprite needs to go in a region of PPU memory, a video memory called OAM, Object Attribute Memory. So OAM is essentially like a hardware display list that the PPU will read when it's drawn. Each entry in OAM is 4 bytes, indicating data about the sprite, and the PPU will draw all those sprites on the screen. But because OAM is stored in video memory, it can only be accessed during blanking periods, like we were talking about earlier. And so the way the game handles this is it keeps a CPU-side buffer of all the sprites that need to be drawn to OAM. And then during vertical blinking, in between frames, it uses DMA to quickly transfer this buffer over to OAM. That way the gameplay routine can take its time well in the middle of a frame, figuring out, running all the physics, figuring out where all the sprites need to go. It'll output the sprites into this buffer as it goes. And then during the very short interval of time between frames, then you don't need to run any logic. You just have to quickly copy that buffer over. Now, in 2020, SNCC found an interaction known as the pose glitch. As we saw before, there's a lot of pose glitches, but this one's weird enough that it gets to be the pose glitch. So if we manage to trigger these 3 specific pose transitions all on the same frame, the first one being the knockback that you take from getting hit by an enemy runs out. So you get hit by an enemy, here's the enemy, here's you. You run, you get knocked into the air, and then you start to fall down. When that knockback runs out, it wants to put you into that falling pose. Now, when Samus lands on the ground, it does a little landing animation where she kind of does that, and then stands up. So when the landing animation finishes, it wants to transition Samus into a standing pose. And then when you press jump, well, that triggers a transition into a jumping pose. It turns out that because of some quirks in the priority system for pose transitions, if you trigger all of these on the same frame, they all cancel each other out and no pose transition happens. This is the relevant bit of the code. This is a disassembly created by a reverse engineer named PJ Boy. This is the code for the knockback transition. Basically what happens here is it sees that because you landed on the ground, the knockback is no longer active, and so it aborts its attempt to put you into a falling pose. The landing transition sees that you are trying to jump, and so it decides not to put you into a standing pose because that would eat your jump input. And then this knockback transition actually takes priority over jumping, which means that your jump doesn't actually occur. So the end result of this is that no pose transition takes place at all, and the game stays in the landing pose, and it just advances to the next frame of the landing pose. The problem is that landing pose is just like that turning around animation, where it's a few animation frames for the landing, and then it just ends with a pose transition. But we've reached the end of the landing animation, and we've stayed in this pose. What happens? Well, we get a buffer overflow. We start reading past the end of this pose as data. Specifically, we very intentionally landed in this pose, which is hex E5. The name of this pose is facing left, landing from normal jump, aiming down left. In this pose, the reason we chose this is because immediately after this pose in memory is the animation data for a special pose that only occurs during a cutscene. And this pose looks like this. This animation looks like this. Basically, Samus is in the air, she falls to the ground, and then collapses to her knees. The way this is implemented is using a special animation instruction. It's this F7 byte here. That instruction in the animation delay table says, when Samus touches the ground, skip to frame 7 of the current animation. The idea is that this animation, it plays, it has this loop where you're just falling, and then it triggers that special instruction so that when you touch the ground, it'll break you out of the falling part of the animation. It'll skip ahead to this little loop here, which is the crouching animation. Now this animation, particularly is this special instruction. The special F7 instruction is only ever used by this animation. It's not intended to be triggered while the player has control over Samus. It's only intended to be triggered from this cutscene pose E8. But instead, we triggered it from pose E5 during normal gameplay when we have full control over Samus. And it behaves a little bit buggy in that situation. if we manage to trigger a pose transition on the same frame that we touch the ground and that F7 instruction runs, then we go to frame 7 of the new pose that we transitioned to, instead of the intended frame 7 of the whatever of this E8 pose. So this actually allows us to get buffer overflows in most poses. So we figured out how to get a buffer overflow out of a landing animation. Now if we do this, most poses don't have 7 animation frames. So by triggering this pose glitch and then transitioning to another pose at just the right time, we can skip out of bounds in most poses. This allows us to access a lot of different unused or invalid animation frames, like animation frames that just should not be run in the context that they're being run. Some of them which don't even exist. And some of them don't have a sprite map associated with them, which means that the sprite map pointer is set to null. Now, there's no null check in the routine which draws a sprite map to the screen. So we have a null pointer dereference. But we're on a system that doesn't have virtual memory. It doesn't have any kind of memory protection at all. In fact, memory address 0 is just RAM. So when we dereference a null pointer, we just read data out of RAM. Specifically, memory address 0 is often used by the game to just store various bits of temporary stuff. So there's a lot of different things that can go in that address. And we can actually have some control over what's there by activating this glitch under different scenarios. Now, if this happens, and particularly if memory address 0 happens to contain a pointer to somewhere within the ROM, we're going to try to read that, and we're going to try to interpret it as a sprite map to draw. But when we do that, like remember that the beginning of a sprite map in memory is the number of sprites in the sprite map. And so if memory address 0 has a pointer to somewhere in ROM, then that pointer gets interpreted as the number of sprites in the sprite map. And since it's a pointer in ROM, it's probably like in the tens of thousands. And so now the game will try to draw tens of thousands of sprites to the screen. And that's actually what's happening in this short little clip. We trigger a pose glitch, and then all of a sudden the game slows down so much that it's drawing like 1 frame every 2 seconds. That's because that's how long it takes to draw tens of thousands of sprites, trying to draw tens of thousands of sprites each frame. This condition has been known for probably 10 or 15 years, much longer than the pose glitch itself, because there's a couple of other ways to, as I said, there's a lot of pose bugs, there's a lot of animation bugs in this game. There's a couple of other ways to get into this situation. Normally for speedrunning, it's a bad thing because it slows the game down so much. It's been known to happen to runners running 100%. There's a glitch you go for at the end of the game, and if it goes really badly, it can cause this situation. So it was just like never really thought to be that interesting until this March, when Snick was just glitch hunting. He was experimenting, trying some different things, trying some different combinations of scenarios that were known to be buggy, and trying to see if he could get anything interesting to happen. He triggered sprite lag, and then his game suddenly crashed. And we looked to see why, and, well, essentially, the cause of the crash was in the routine that tries to draw a sprite map into the buffer that will eventually get copied to OAM. The way this routine works is we start out by reading some data from the beginning of the sprite map, like the number of sprites in the sprite map. We use that to set up a loop counter. Then we go and we copy the X position from the sprite map. We add to it Samus's X position on the screen, because the X position is relative to the center of Samus. We write that into OAM. We have some checks based on like the position and the size of the sprite. If the sprite is way off the right side of the screen, or if it has a certain size bit set, then we need to go and modify a couple of bits in the OAM. So it has some branches for that. We also do the same thing with the Y position. We take the Y position of the sprite in the sprite map, we add it to the Y position of the sprite map center, we put that in OAM, we copy over the tile number and the attributes, and then we advance to the next sprite in the sprite map, and we advance to the next sprite in the OAM buffer. So each sprite map is 5 bytes, so we add 5 to this pointer, which is stored in the Y register. And each entry in OAM is 4 bytes. So we have a pointer that stores the next free entry in OAM. So, and this pointer is persisted across when we draw multiple sprite maps. So like, you draw an enemy here, and then you draw Samus here, and then you draw an item here. as you keep drawing things, it's not gonna overwrite the same sprite in OAM. It'll keep putting them one after another in OAM, and all the sprites will show up. Now, you might be thinking, well, if we're trying to draw tens of thousands of sprites, do we have a buffer overflow? No. That's what this bitwise and is for. It's a bounce check, so no buffer overflow, sadly. Developers thought of that. But what they didn't think of has to do with how this addition works. You see, this is an ADC instruction, not an ADD for add. This is add with carry. If you guys have done assembly programming before, you might be familiar with that instruction and what it does. Essentially, it's an instruction designed for creating multi-word addition by chaining single-word additions together. So the idea of how it works is you add two numbers together. If the addition overflows, then it sets a bit in the processor status register called the carry flag. And then the next time you do an ADC instruction, if that carry flag is set, it adds an additional 1. So that way, like, it's for chaining additions of smaller units together. If one overflows, then it carries into the next. Now on the 6502 family of processors, there's actually no regular add instruction. There's only an add with carry. Whenever you want to do a regular addition, which is most of the time, you have to explicitly clear the carry flag first. That's what this CLC instruction is for. So we clear carry, we add 5 to the sprite map pointer to go to the next sprite, and then we add 4 to the OAM pointer to go to the next entry in OAM. Except there's no clear carry flag here. That's because that's not really a mistake on the part of the developers. It's because they said, oh, this addition here is a pointer within ROM. We're going to the next entry in a table in ROM. There's no way this is ever going to overflow past the end of ROM, right? Well, what happens when we try to draw tens of thousands of sprites? It overflows past the end of ROM, actually several times. And what that does, there's a bounce check here. All it means is that now our pointer in the OAM is not a multiple of 4 anymore, which on the face of it isn't that interesting. Like, it just means that now our sprites are going to be corrupted because, like, maybe the Y position is drawn where the X position is supposed to be, and the attributes are drawn where the tile number is supposed to be. Like, so what? Like, the screen looks glitchy now. Well, there's this routine that is called at the very end of the frame before the OAM buffer is copied into video memory. See, the developers were clever. They said, well, we could, at the beginning of the frame, clear the buffer before we render sprites into it. Or we could actually just leave the buffer stale, and then we'll render sprites into it. We'll overwrite the stale parts. And then at the end of the frame, we only have to clear out the entries that weren't used. So that's a performance optimization. There's another performance optimization here, which PJ Boy aptly describes in his comment as one hell of an unrolled loop. The idea, so this loop for clearing out these sprites is just unrolled 128 times. 128 sprite slots, and so this store A instruction that clears out a sprite slot is repeated once for each sprite slot. And then what they did that was really clever, we don't want to clear out all the sprites, we just want to clear out the ones that were used. And so we take this pointer, that's the pointer to the next free sprite slot, and we look at it and we see that, okay, this pointer is a multiple of 4 because there's 4 bytes per sprite slot. Each of these store A instructions is 3 bytes in size. And so we take the OAM pointer, we multiply it by 3/4, and then we add that to the memory address at the beginning of this loop, and then we jump to that spot in the middle of the loop. This is a pretty clever optimization, and it means that you don't have to have like any loop control logic, so this loop runs way faster than it would without it. But what if our OAM pointer is not a multiple of 4? Well, then we can jump into the middle of an instruction. If it's not a multiple of 4, then this calculation might produce a value that's not a multiple of 3. And so, like if the OAM pointer was 16, that means we're at the start of the 4th sprite, we jump here. But if it was 17 or 18, we might end up jumping here to this byte instead. Now on the 6502 processor, every instruction is formatted as a 1 byte opcode that indicates what the instruction is, followed by 0 or more operand bytes. So if we jump into the middle of instruction, we're executing operand bytes as if they were opcodes and vice versa. You'd think that this would let us do a lot. Like, look at all these different numbers in here. We can run so many different instructions if we can control where we land in this loop. It turns out that every single one, there's 128 of these stores, and there's 2 bytes per store, so all 256 of these opcodes don't do anything useful. Which is like, really? Come on. Except that if we manage to land, there are 2 spots. I think one of them is right here, and one of them is right here. Like this byte or this byte. If we manage to land at either of those bytes in the loop, then we actually get something interesting happening. So for our exploit, we precisely manipulated the behavior of the enemies in the room and Samus, and fired some shots and collected some drops and stuff like that, so that we would have the exact right number of sprites on the screen, so that when this exploit happened, when this bug happened, we landed right here on this byte. And here's a CPU trace of what happens next. So this byte 05 is the opcode. It's the ORA opcode, or accumulator. It's a bitwise OR. It doesn't do anything particularly interesting, but it treats this 9C as an operand, and then we end up at this 90 byte. That byte is branch of carry clear. The carry flag right now, that's this one. It's lowercase, which means it's clear. And so this branch is actually taken. We jump ahead somewhere further on. The spot that we end up jumping is actually right after this return instruction and at the beginning of the next routine. Now, right now on the stack, we have the return address of the sprite drawing routine, which is 828975. Or let's do it like this. 828975. And then above that on the stack, this routine, when it was called, it pushed the processor status onto the stack to preserve it for the caller. That was 0, 0. So our stack looks like this. And then this routine is supposed to end with a pull processor status to pop that byte off the stack, and then a return. But instead, we go to the next routine. And the next routine expects it's going to be called with a return address on the top of the stack, because that's how function calls work. But instead, when this routine returns, what it does isn't even important. All we care about is what happens when it returns. And it ignores this, and it returns to address 897500. So 89 is the bank, 7500 is the address. If you have a really good memory, you might remember that I mentioned earlier that the MMIO registers go from address hex 2000 to hex 6000, and then the ROM starts at hex 8000. 7500 is in between those. There's a gap there. That memory is not mapped. Now, obviously on a modern computer, if you try to read from memory that's not mapped to anything, you get segfault, crashes. But again, we don't have memory protection. So what happens when you try to read from a physical address that's not mapped to anything? Well, the way that memory works is there's a bus coming out of the CPU that goes to all the different peripherals. When the CPU wants to read from a memory address, it'll put an address on the address bus, and then whatever peripheral is mapped to that address will respond with data on the data bus. If there is no peripheral that's mapped to that address, then no peripheral will respond. And the data pins going into the CPU are just not driven by anything. They're floating. You're trying to read from an input pin that's not connected to anything. That's a condition that we call open bus, because literally the bus pins are open. They're not connected to anything. It's like an open circuit. It's not a closed circuit. And in order to talk about what happens there, we are now leaving the realm of digital logic, and we have to look at analog effects. So think about the layout of a bus on a circuit board. You have these big, long conductors that run across the whole circuit board and go to all these different peripherals. Then under that, you have this really thin insulating substrate. And then under that, you have the PCB's ground plane. So you have a big conductor, then you have a really small insulator, and then you have another big conductor. Do we have any electrical engineering people in here who can tell me what that gives you? Exactly. So this effect is, electrical engineers call this parasitic capacitance, because usually it's bad. Every bus is always going to have a little bit of capacitance to it, and that limits the speed that you can move data across this bus. And electrical engineers will try to minimize this in their design. Here, we actually have to use it to model what the circuit is going to do now. Because the bus behaves as a little tiny capacitor, if we try to read from it when there's nothing attached on the other end, it'll tend to remain at whatever voltage it was at before. So this means that if you try to read from an open bus, if you try to read from unmapped memory, the byte you get back is usually whatever data was last sent over the bus. In this case, the last byte that we read from memory was this 8-9 off of the stack. And when this routine returns to unmapped memory and we start trying to execute code from unmapped memory, the CPU goes and it tries to read an opcode from address 7501. That's unmapped. It gets the byte 8-9 back, because that's the last byte that the CPU read from memory. That byte is a bit test opcode. Doesn't do anything particularly interesting. It reads an operand byte from 7502. That also gets 8-9, because nothing new has come over the bus since then. Next instruction runs, 7503. We read that. It's also unmapped. We get 8-9 again. It reads this operand. We get 8-9. Read the next opcode, we get 8-9, 8-9, 8-9, 8-9, 8-9, 8-9. And we just keep doing that. We keep going on and on and on until eventually the program counter gets all the way to address 8000, which is where ROM starts again. Now, as I mentioned before, this is extremely precise to even get to this point. You need an exact number of sprites on that screen. And it turns out that once we get there, it just kind of crashes. So this bank 8-9 is full of graphics data, not code. And so we try to run this graphics data at code. We get nonsense. It's not long at all before we execute a 0 byte. And on the 6502 family of processors, the 0 byte raises a software interrupt, and the game handles the software interrupt and crashes. Processor designers, if any of you in here design processors, please don't make opcode 0 crash. That makes it so hard to exploit things. But it turns out, we observed that we were executing the odd addresses as opcodes and the even addresses as operands. And so this meant that the first byte that we actually executed, this last bit instruction we read from 7FFF, and it reads an operand, a byte 2C, from address 8000. And then it treats 8001 as this branch opcode that leads us off to the crash eventually. So if it was somehow possible to be executing even addresses as opcodes here, we actually get a different behavior. Specifically, what happens is we do a couple of nonsense instructions, and we end up jumping to address 893838, which is also open bus. That's not mapped to anything. It's in the middle of the MMIO space, though. And it's interesting because the controller input bytes are stored at address 4218. That's not that far. That's like a few kilobytes of unmapped memory. But if we can somehow get the program counter to execute all the way through that space without crashing, it'll eventually get through the region where the controller input bytes are stored. And if that happens, we win, because we can push whatever buttons we want on the controller. We have full control over those bytes. We can put any code there. So the problem is that, unless we have some way to actually get the processor to execute this address instead of this one, then that's no good. So we need some way to influence what instructions are executed during this open bus period. Maybe some kind of a hardware thing that would suddenly, suspend the CPU and take over the bus for some reason. Remember I mentioned the DMA controller can suspend the CPU to take over the bus so it doesn't cause a bus conflict. And remember that I mentioned that the CPU has the ability to schedule DMA transfers to occur in the future at certain points during the graphics rendering process. And it turns out that one of those transfers is scheduled for about 2.8 milliseconds after the crash happens. So if the crash happened about 2.8 milliseconds later, then while the CPU was on open bus running those 89, 89, 89, 89, 89, then the DMA would kick in, it would pause the CPU, it would use the bus for a little bit, and in the process, it would leave a different value on the data bus, and we'd run some other instruction. The problem is that, well, we have to somehow get that crash to happen 2.8 milliseconds later. And like, we don't even know if we can get it to work. We know that maybe if it worked, we could get to address 3838, but that's a long way from 421 it. So at this point, I used a memory editor to create a modified save state to simulate what would happen if the game behaved exactly like that, except the crash happened later. So just to answer the question, is it even possible? And what we found is that most of the MMIO space is either unmapped or write-only, because most of the MMIO registers are for the CPU to send data out to peripherals. The CPU isn't reading all that much data in. It turns out that there are only 10 registers between us and the controller input that are readable. This means that if we manage to get stuck in one of those open bus loops where we're just reading the same data over and over again, we can just cruise for a while as long as we don't run into any of these, as long as we don't run into any problems with any of these 10 registers, because they'll change the value that's on the bus. Another thing that's worth noting is that a lot of input registers don't actually put data on all 8 data lines. They just use like 1 or 2 bits and leave the rest open bus. This is because, this is just for simplicity in wiring those. They just aren't connected to all the data lines. If you look at the hardware documentation that Nintendo probably gave out to their developers, it would just say that the rest of the bits are undefined, don't look at them. Because we know how the hardware works and we know how Open Bus works, we actually know, oh, these bits are just going to keep whatever was the last value transferred over that data line. So if we manage to get that HDMA to interrupt the Open Bus execution, what happens is we end up with the value CA on the bus, which is the opcode for decrementing the X register. And that instruction doesn't read from memory, and so we could just cruise through Open Bus running that same instruction over and over again. The CA instruction has the bit pattern 1100, 1010, I think. And then when we get to this address here, 4016, that leaves these top bits untouched, and it sets these bottom bits to 0, 1. That instruction is a compare instruction, which doesn't do anything particularly interesting. And then this next one, which is read as an operand, sets the bus to the value DD. Because it changes some of the bits and not others, that's the value that's left on the open bus. Now, the opcode DD is a compare instruction. And this compare reads from memory, and the memory address it reads from is dependent on the value in the X register. And remember that the HDMAs that occurred earlier left a decrement X instruction on the bus. And so this means that the exact timing of that HDMA is now important, because the value of the X register influences what memory address we read from, which influences what value we're going to get from reading, which influences what's going to be the next value on the open bus, which influences the next instructions that are going to be executed. This is sort of both good and bad for us. It's good because it means we have some more control over what happens on open bus by manipulating the timing. It's bad because it means that now we have incredibly precise timing in order to get the right things to happen. So I'm going to kind of fast forward through this a little bit because of time. But basically, these addresses the addresses immediately after don't cause too much trouble. There's a chain of a few different instructions that happen until eventually we get stuck in a loop of instructions that don't touch memory, and so we make it all the way down to 4210. This one's annoying. This part's annoying. Well, this one's not too bad. This one, when we execute it, it reads the value 42, which is the only instruction in this processor's instruction set that is undefined. Its abbreviation is WDM, which is after the processor's designer, William D. Mensch, Jr., and it just does nothing. It's a 2-byte no-op instruction. But it leaves 42 on the bus. And that's really annoying because of this register down here at 4212. When we try to execute that, almost all the time, it clears this bit up here, which is that 4. And it leaves a value of O2 on the bus. O2 is another opcode that raises a software interrupt, which means the game crashes and there's no hope of beating it. But this is actually a rendering status register. And this bit will be set if we read it during the horizontal blanking interval, which is that interval between when the graphics card is drawing 2 lines of the picture. That window is 12.8 microseconds wide. That's about 34 clock cycles. And that's on top of the specific timing window needed to have the right value in the X register, and also that 2.8 milliseconds that we have to deal with in order to get that H-blank to happen while we're crashing. It would be a lot easier if we could come in aligned on like an odd address, and this was an opcode, and this was an operand. But then that would break because we got 0 bytes here. We got a lot of 0 bytes here. So we absolutely need to run a 2-byte opcode right here, which means that we absolutely need to be in horizontal blanking here. That will get us down to this byte. And these bytes are the processor's division results. The last time it did a division was when calculating the position of this energy tank in the room. Fortunately, the X and Y coordinates of this energy tank happen to decode to valid 2-byte instructions. So this is a valid 2-byte instruction, this is an operand, this is a valid 2-byte instruction, this is an operand, and we never execute a 0 at all. We don't crash. So at this point, finally we're there. We're finally at address 4218. We can run controller input, and we can just literally put in our shellcode by holding buttons on the controller. We can plug in up to 4 controllers. Each can have up to 16 buttons. So that gives us 8 bytes of code to work with. We came up with this payload that basically fixes up the stack so stuff doesn't crash. And then it jumps into the middle of this routine that is responsible for setting up the end game cutscene. So if we execute that payload, we win. But we still have the problem that we have to figure out how to deal with those 2.8 milliseconds. The crash occurs way too early. 2.8 milliseconds is a lot of processing time. And not only do we have to figure out how to get the crash to happen later, we have to get it to happen an exact amount of clock cycles later, basically. So what in the world could possibly use up 2.8 milliseconds of CPU time? What is there in this room that we can change to increase the amount of processor time that is consumed before the crash? And the answer is that there's some enemies in this room. And we might be able to manipulate their behavior to use up some more CPU time. These guys are called BTOMs. This is a flowchart of how their AI works. It's not that complicated. Basically, when they initialize, the first thing they do is they disable off-screen processing. That means that they will only tick while they're on the screen. That's really annoying because we have to have an exact number of sprites on the screen in order to trigger the crash in the first place, because of how it involves the sprite drawing routine and how we have to jump. We have to jump into that exact right spot in that big unrolled loop. Specifically, that means that those sprite requirements mean we can only have 1 BTOM on screen at a time. But if the BTOMs do a lunge or a leap, then they will be able to process off screen for a little while. That's so that if it starts jumping and you go off screen and then you come back, it wasn't just hovering in the air the whole time. It's finally landed on the ground. The way the AI works is they have this kind of main choose AI state. If Samus is nearby, they go to a lunge towards Samus. If Samus is far, then they call the random number generator to decide whether they'll just sit idle for a little while or they'll just leap up in the air. Whenever they do a lunge or a leap, as I said, they enable off-screen processing, and then they move around according to the parameters of that lunge or leap until they collide with something. If they collide with a wall, they disable off-screen processing, and then they fall to the ground, and then they go back to choose a new state. If they collide with a floor, they go back to choose a new state, and they don't disable off-screen processing. I think that's probably an oversight on the part of the developers. It means that if a BTOM starts jumping around, then it can leave the screen, and it'll continue jumping around off-screen until it bonks a wall. That's good for us, because we can manipulate both this by deciding whether or not we want to be within 6 tiles of the BTOM. We can also manipulate RNG. This is because the game's random number generator continually cycles in the background. And so by inserting like strategic pauses, like just waiting a little bit here and there, then we can force the RNG to cycle until it has a value that is favorable to us and will make the BTOMs move the way that we want them to. As a result of this process, I do not like BTOMs very much. And that's an understatement. I really do not like BTOMs. I searched chat logs between me and Snick for just all messages mentioning BTOM, and this is just a big sample. We spent probably 100 or 200 hours figuring out how to get the BTOMs to do what we want them to do. Every time we would try to like figure out something to do to make the room faster, it would almost work, except the BTOM would get in the way. Yeah. Yeah. So, wrapping it all up, this is the list of things that need to happen in order for our exploit to work. We need to burn 2.8 milliseconds while having an exact number of sprites on the screen. In order to burn that much time, we must have at least 4 of the 5 BTOMs in the room actively in the middle of a jump while the game crashes. Because while they're jumping, they do collision checks that add extra processing. We also have to have exactly 1 BTOM on the screen, no more, no less. That means that 3 BTOMs must all be processing off screen, and those 3 BTOMs can never touch a wall. The BTOMs must also never touch Samus, because if they do, then that changes some sprite priority flags, and that makes the sprite lag exploit not work anymore. We also need to have exactly 1 bug on screen. There's these little bugs that spawn out of the pipes. We have to have a shot exploding on the screen. The screen has to be fading out for a pause. We also have to fire a shot before the frame of the crash to create additional processing work. We have to press item select the frame before the crash. Again, that reloads some graphics, which does more processing. Finally, we also have to have Samus drawn close to the right side of the screen. The reason for this is something that I mentioned a little bit earlier. In the sprite map drawing routine, if a sprite is placed way off to the side of the screen, then it has an extra branch that it does that sets some bits in the sprite's flags for the graphics hardware. While the game is drawing tens of thousands of sprites to the screen during sprite lag, if Samus is just a couple pixels further to the right, then that means that a couple hundred more of those random memory addresses that get interpreted as sprite coordinates are going to end up meeting that threshold to be off the right side of the screen, which is going to cause the extra branch to be taken. That's going to burn like 6 CPU cycles or something like that each time, which, over the case of tens of thousands of sprites, adds up to like a couple hundred CPU cycles, which is not a lot, but we need it. So now that we actually understand what's all going on, we can watch that last room again and actually see what's happening. So the first thing that's going to happen, and I displayed the gameplay in the middle, some memory watches on the right, and then the inputs on the left. The first thing we're going to do, once we fall down here, we're actually going to stop and wait for 4 frames, because that'll cause the RNG to cycle. You can see that here. There's that 4-frame gap in our inputs that'll cause us to get better RNG from the BTOMs. You can barely see it when you're watching. That's in slow motion. We just stutter just a little bit right there. Then we navigate the spike tunnel. Now, that RNG manipulation was to get that guy to jump up and to the right. Remember that if he is within 6 tiles of us, he will do a lunge towards us. This is 1, 2, 3, 4, 5, 6. We are barely not going to get lunged. And that would be bad if he did, because then he'd end up way too close to this wall and he'd end up bonking it later. Next up, we're going to, once we land on the ground, we're going to stall for 2 more frames, again for RNG manipulation. And then we're going to do a jump up and damage boost off of this spike. Now, notice how we are just to the right of this BTOM right now, right as he landed. That means that he's going to choose a new AI routine, and because we are within 6 tiles of him, he's going to try to lunge towards us, and because we are like a pixel to the right, he's going to lunge to the right. instead of to the left, which again would have caused him to bonk that wall, and then our exploit wouldn't work. Next up, we got that BTOM to jump that way, which is nice. We shoot that bug. We're going to fire one more shot to kill the bug. The reason for that, there's two reasons why we want to kill that bug. Number one, our health is really low. We have 19 health, and each spike does like 12 damage, I think. And we need to take 2 more spike hits. We don't have enough health for that. The second reason is that, so when we kill it, it'll drop health that we can use to take more spike hits. The second reason is that we need to have a bug on screen when the crash happens, and killing this bug now will allow the pipe to spawn a new bug so that it'll actually be on screen, because this one would go and fly away. This BTOM, I don't remember. I think we manipulated him to sleep here for a little while. We're gonna fire a shot to kill that bug, and we're gonna do another damage boost off those spikes. And this damage boost was very particular. You can influence the trajectory of your damage boost by changing what buttons you're pressing. If you press forwards, then you get a downwards boost. If you're letting go of forwards, you get an upwards boost. And then when you press backwards, then you actually start flying backwards. So we did a downwards boost with a delayed backwards press, so that we went like all the way down here before we started flying backwards. That's all done to manipulate the screen scroll precisely, so that we just barely bring that guy on screen and activate him. Now that he's active, he'll start doing his thing, jumping around. And this damage boost was also really helpful because the game likes to put Samus towards so that she's facing, so that there's more space in front of her. So if Samus is running this way, if she's running to the right, if she's facing right, then it'll try to put her towards the left side of the screen so you can see what's in front of you. And if she's facing left, like she is now, then it'll try to scroll the screen this way so that Samus goes towards the right side of it. That damage boost helped a lot. She would have been like over here without it on screen, but that's still not far enough. And so Snick came up with a strategy of landing on this platform and rapidly alternating between walking forwards and moonwalking backwards just to give the screen some time to catch up. When we do that, you can see how much the screen scrolls. Samus is so much further to the right now. This BTOM is about to grab us in 17 frames, to be precise, when our invincibility runs out, so that's bad. But what we do now is, that's a trick called a flatly jump. So the turning around animation in Super Metroid is considered uninterruptible. That means that it won't get, like you can't really change out of that pose, usually. That's done so that like if you're running off a platform or if you run into something and you've just barely started to turn around, Samus doesn't like instantly snap. She'll finish the turning around animation first. Now, since Samus is in a turning around on the ground state, when she runs off the platform and she falls off while turning around, she starts to fall, but she's still in an on the ground state, which means she can jump. So that lets us jump from right here instead of right here, which is kind of weird. You're jumping out of midair, but it's kind of a cool thing. The reason for that is so that we have a very specific vertical positioning that wasn't achievable. Well, earlier versions of this task, we had to jump like way up here in order to get the right vertical positioning. This is way faster by like 10 or 20 frames, which is a lot in this context, especially when the BTOMs are being annoying and you have to figure out how to dodge them fast enough. Next up, we turn around and do a wall jump check off of this block. We don't actually wall jump off of it, but getting into this wall jumping animation aligns our subpixel position with the edge of this block, which is helpful because now our vertical position and subpixel position, our vertical subpixel and horizontal subpixel positioning are perfectly, like subpixel perfectly aligned exactly where we need them to be for the next part. So now we're gonna get hit by this spike, and because of the subpixel positioning, we can actually damage boost and land up on this pipe. Now we are in a state where the landing animation is just about to finish. Samus's knockback is just about to run out. You can see there's only 1 frame of knockback left. And we are about to press jump. That will trigger the pose glitch. So now obviously the pose starts glitching. We fire a shot because we have to have a shot exploding for our exploit. We press down, left, and right to jump to frame 7 of a specific pose that we chose because it will both draw a null animation frame and it also has other properties that lead to the right number of sprites being drawn on the screen. We tried a bunch of different poses, and that's the only one that would work in this situation. And then we pressed pause to pause the game so that the screen would start to fade out. Now sprite lag happens, the game slows down to 1 frame per couple of seconds. And then the frame before the crash, it's a very long frame. It's a frame that lasts for lots of real-time frames because the game is drawing 1 frame per couple of seconds. We press item select and we press shot to increase processing time. We also press the run button. And then once the game's on this last frame, we hold a bunch of different buttons on all 4 controllers. This is again because of that check in the sprite drawing routine that will go and do some extra stuff if a sprite gets placed way off to the right side of the screen. When it's drawing tens of thousands of sprites, it reads from all of memory, including the MMIO registers, including the controller input. So the controller input actually gets drawn as sprites. And pressing all the buttons on the controller all at the same time means that, or not all of them, we had to be kind of careful. Some of them are not pressed because that changes how the overflow behavior works and stuff. But pressing a lot of buttons means that when the controller input gets drawn as sprites, they get placed way off to the right of the screen, which means that extra branch has to be taken, which adds a dozen or 2 clock cycles, which we actually needed. We were within 6 clock cycles of our exploit not working at all. So finally, at the end of this frame, this is our shellcode on the controller input. And that's the run. Let's watch that last little bit one more time in real time. Tiny little pause for RG manipulation. One more tiny pause, jump, damage boost, get the V times to go where we want them, kill the bug, get the drop, do the pose glitch, hold a bunch of buttons, put in our shellcode, and we win. So that's the run. Thank you guys so much for listening. I want to give a huge thank you for SNIC for inviting me to work on this because this is one of the most fun things that I've ever done. It's also by far the hardest thing that I've ever done on a computer. It was many hours of hard work. I remember the first time that I actually got to see code executed from the controller port. In the test environment where you had the hack save state, mind you, just to figure out if the timing would work, I was actually in a conference room in Kelly with Lucas and Gabriel and Alan, I think, and I probably jumped out of my chair or something. Yeah, this was an awesome project and something that I'm really proud of and I'm really excited to have been able to show you guys, so thank you. I also want to just thank the whole Super Metroid community for being really cool. If this kind of thing is something that you guys are interested in, I highly recommend you check out Super Metroid or even any other speedrunning community where people do stuff like this because there is so much opportunity for just experimenting with things, playing around, building up your computer skills, and occasionally getting to do a fun project like this. One thing I will point out is that this was my first time exploiting a real-world system rather than something created for a CTF. And it was really interesting to see what that was like. Because for a CTF, you always you get lucky with how the memory layouts are and how all the functions are written and everything just kind of happens to fall into place so that you can pull off an exploit. Because somebody was designing it so that you could pull off an exploit. With this, we had no idea until we actually got full arbitrary code execution whether it was even possible. At no step of the way did we say, okay, it's definitely possible now. It's okay, we've overcome one obstacle, but there's still 10 more things that might just not be possible to get past. If the coordinates of that energy tank hadn't been valid 2-byte opcodes, we might not have been able to get past it. There might have been some things we could do collecting the energy tank and then interacting with the door or something like that was an idea we had, but who knows if that would have even worked. There also were times where we did get lucky. Like if that sprite leg loop had done those 2 additions in the wrong order, or in the other order, then we wouldn't have had that carry bug and none of this would have been possible. If the room didn't have the exact right arrangements of BTOMs and sprites and bugs and the values of the poses didn't all work out just right, none of this would have been possible. So sometimes we got lucky, sometimes we got really unlucky. The 256 opcodes all not being good was another one of those. But I feel like what I learned from that is that when you're exploiting a system, you really just gotta make your own luck. Like sometimes stuff will work, sometimes it won't. You have to be determined, not give up when you hit an obstacle, and just think outside of the box. Maybe you can use some weird timing DNA thing in order to get around it. So anyway, that's all I had prepared. Thank you guys for listening. I know it's late, so if you have questions, you can ask them, but if you want to leave, you can do that too. Thank you guys.